Hi guys, today we are going to talk about Einstein's special theory of relativity. See, so the whole theory comes from the fact that the speed of light is constant. So what does that mean? To understand that, we need to talk about relative motion. Imagine a man. Let me take a different, let's take this pen here. Imagine a man. He's sitting here. He's just standing here and there is a train. There is a train in which there is another man sitting inside the train. So the train is moving this way at, let's say, 5 miles per hour or 5 kilometer per hour. 5 kilometer per hour. So according to this man, I'll call him A, and we call this man here A, and I'll call the one here B. So according to A, the train is moving at 5 kilometers per hour, and so is B along with A. But for B, he does not feel that he is traveling at 5 kilometers per hour. He feels that A and the entire world is traveling in the opposite direction at 5 kilometers per hour. Now you can say that only A is correct. Actually wrong. Both are correct. Both are correct at what they are measuring. So you can argue that A is correct because the train is obviously moving. But I can tell you that that is wrong, because imagine a universe where there is nothing. It's all empty and there's only darkness. Now there is A sitting here and B is moving past A at 5 kilometers per hour. Now there is nothing to compare with if A is moving or not, or B is moving or not. Yeah, this is B and this is A. For him, according to A, B is moving because he sees B moving relative to him. But for B, he feels that A is moving. You can't tell which of them are wrong, because if you go and look at their frame of reference, it would look exactly as if A is moving or B is moving, because there's nothing to compare with. There's no way you could prove who is moving. So this is the concept of relative motion. There is no thing called absolute motion. Everything is relative. It depends on the frame of reference. So now let's talk about light. The speed of light, represented by c. This is the speed of light. C is equal to 299,792,458 meter per second. Now this speed is constant. Experimentally, it has been proven that c is not relative. The speed of light is not relative. However fast you go, the speed of light remains the same. Now that brings Einstein and his great mind, which invented special relativity. So idea is this. The idea is that imagine a man is moving at, let's say, very close to the speed of light. Let's say 200,000 meter per second. And now imagine a flash of light going here. There's a flash of light. It's going past him. Now since the speed of light is constant, he cannot, and he is moving very close to the speed of light. So he should be seeing that the light is moving slower than 300,000 per second. But he does not see that because the speed of light is constant and it does not change due to relative motion. So what does this mean? Now let's say, what is speed? If you remember, speed is equal to this distance by time. And now the speed is constant. Speed is constant, and now now to keep the speed constant, what must we do? The speed is trying to slow down here. But how can we increase that? See, so when this man is looking at the light, he should be seeing the light slowing down, but that does not happen. In order to accommodate for that, it must mean that time must decrease. The time must decrease because speed is inversely proportional to time. Time must decrease in order for speed to increase and keep speed of light constant. So time decreases for whom? The man. That is, he experiences less time than a stationary observer here. This observer, the yellow observer here, I'll call him B and A again. So A experiences less time than B. That is, he ages less. If B and A have have clocks, and A starts moving to close to the speed of light and B is stationary, and they check their clocks after A stops moving, then the time of A would be different from B because he experiences less time. Now, not only does the time decrease, but the distance between 2 points near for A also decreases. Now let's say if B says that there is 5 meters, or let's say 5 kilometers between 2 points, but for A that distance will actually not decrease but increase. It will increase because the decrease in time is not enough to accommodate it for the constant speed of light. So the distance will increase. A will measure more than 5 kilometers between the 2 points. Very interesting, right? And these effects have been experimentally proven. Now we are going to talk about E is equal to mc square. So this is one of the most famous equations. Many people know it, but they don't know what it means. They have no idea what it means. So this equation is quite simple to understand, but its derivation is too hard for this video. It's too complicated for this video. So E here is equal to energy. Simple energy, and mass. M is mass. And as I told you right now, C here is the speed of light. C is the speed of light. And C square is obviously speed of light squared. Speed of light squared. Now, so why is this equation useful? Now let's say, this energy can be interpreted as the energy required. Energy required to move, and mass, speed of light squared. Energy required for what? Moving at a certain velocity, you can say it can be any activity. And now, because our activity is moving at a certain speed, we need to consider relativistic mass also. So relativistic mass, represented by m with an REL in the subscript, is equal to the rest mass, that is the mass in which it rest, like if you have an object at rest and you measure its mass, that is, you get that to be rest mass. So this is another idea of special relativity. It says that as you increase your speed, your mass also increases. How much does your mass increase by? It is the normal mass into gamma, this factor gamma. So where gamma is equal to 1 over square root of 1 minus your velocity squared divided by the speed of light squared. So depending on your velocity, your mass can change because of that. So now if you calculate your relativistic mass for the speed of light, for your velocity which is equal to speed of light, you get that your mass is infinite. Your mass will be infinity, and because of that, energy required to travel at the speed of light is equal to mass into infinity. For any non-zero mass, that is for anything with mass, it is impossible because you would need infinite energy. You would need infinite energy to travel at the speed of light. So only massless objects like photons, you can say, they don't need energy to travel at the speed of light because their mass is 0. Their mass is 0. 0 into infinity c square is simply 0. So they don't need any energy to travel at the speed of light. And traveling faster than light is impossible because the speed of light, there's nothing bigger than infinity. You need more than infinite energy to travel at the speed of light. Now let's talk about time dilation. So time dilation, you already know what it is. It is just the decreasing of time that we saw earlier. And there is also length contraction, which is the increase or decrease in distance. So time dilation, how much does time dilate? So as you approach the speed of light, for your speed less than the speed of light, time would slow down. Velocity less than the speed of light and approximately the speed of light, time slows down. Time slows down. Now for v is equal to c, time stops. That is, if you're traveling at the speed of light, you won't experience any time. Time just stops. You won't be aging anymore. Your clocks just stop all of a sudden. Now v greater than c, which is impossible, time goes backwards. Time starts moving backwards. Time's backwards. And that's the end of time dilation. So thank you for watching this video. I hope you understood everything. Like and subscribe to my channel. Bye guys.